Why do Transmon qubits need cryogenic temperatures? Imagine trying to listen to a whisper in a noisy room. That's similar to what happens to Transmon qubits if they aren't kept super cold. These tiny quantum bits are very sensitive. They need to be cooled down to temperatures around 10 to 20 millikelvin, which is just a fraction above absolute zero. Why? Because at higher temperatures, thermal energy causes problems. It makes the qubits jump between states randomly, which leads to errors. This is called thermal excitation. If the qubit gets excited by heat instead of a deliberate operation, the whole process becomes unreliable. Transmon qubits are made from superconducting circuits. Superconductivity is a state where materials lose all electrical resistance and magnetic fields are expelled. But this only happens when they are cooled below a certain temperature called the critical temperature. For most superconducting materials used in Transmon qubits, that temperature is very low. If they warm up, they stop being superconducting, and the qubit's quantum properties vanish. This is why cryogenic cooling is essential. Another reason is phonons, which are tiny vibrations in the crystal lattice of the material. These vibrations can interact with the qubits and cause decoherence, which is the loss of quantum information. Cooling to millikelvin temperatures greatly reduces phonon activity. Plus, thermal quasiparticles, which are excited electronic states, also decrease at these low temperatures. These quasiparticles can cause energy loss and shorten the qubit's lifetime. Keeping everything super cold minimizes these interactions, helping the qubit stay coherent longer. Longer coherence times are vital for quantum computing. Coherence time is how long a qubit can hold its quantum state before it loses information. Operating at cryogenic temperatures helps extend this time by reducing environmental noise like thermal photons and electromagnetic interference. This stability allows quantum algorithms to run more accurately and for longer periods. Control and measurement of Transmon qubits involve microwave signals. These signals need to be transmitted with minimal noise and distortion. When the system is cooled, specialized electronics like cryogenic complementary metal oxide semiconductor circuits can operate close to the qubits. This reduces signal loss and noise, making the control more precise. The need for cryogenic temperatures also influences the architecture of quantum computers. Dilution refrigerators are used to reach these ultra-low temperatures. These refrigerators are complex, costly, and requiring a lot of power. They also limit how many qubits can be scaled up because managing heat loads and wiring becomes challenging. Despite these hurdles, cooling remains a must for Transmon qubits to work reliably and accurately. Without cryogenic environments, the delicate quantum states would quickly decohere, making practical quantum computing impossible.